Hello everyone, happy Friday. I'm going to apologize in advance because I know this video is going to be a little bit longer than probably what you would like, but we do have a lot of stuff I want to talk about today. And hopefully with me making this video, it helps you to understand it a little bit better. And then you can go back and watch this obviously as many times as you need to better help you understand this stuff. Okay, so um, we're going to start with the first part of Unit 3. So at this point, you probably already either have seen the notes online, whether or not you're in class or not, or you have picked up a physical copy of them. I'm going to be working on both. Okay, I'm going to be writing some stuff out. I'm going to be writing on the board. I'm going to be doing quite a few things today um, while this video is going on. The way you can hopefully better understand this stuff. Okay, so with that being said, you should open the notes or get out your actual notes and we'll go over this together. Okay. So, so talk about the first one is using and expressing measurements, which is probably the longest section on here. It's got the most content in it. Um, we also have units of measurement and we're going to solve conversion problems. Okay. So if I go out of this real quick to show your learning objectives. Okay. Make sure you are transferring these learning objectives right here. Okay. These first three right here on the screen to the learning objective sheet that's online. Okay. So the three things that we want to discuss today is to be able to write numbers in scientific notations, very important in chemistry. Secondly, evaluate accuracy and precision, tell what they are, and be able to distinguish because students oftentimes get them confused for good reason, but they are definitely different. And the third one is explain why measurements must be reported to the correct number of sig figs or significant figures. But we generally say sig figs because it's shorter and easier to say. So those three things are what we're covering today. So let's go back to this. Okay. So hopefully you've already looked at the Pear Deck or you're planning on opening the Pear Deck and checking these notes other than just what you see in this video right here. Okay, so a lot of times in life, things are determined by the very last second or by an inch or two, no matter if it's a sport or whatever it is. In this example right here, it says sprint times are often measured to the nearest hundredth of a second. Okay, and as a track coach, I've seen plenty of races, whether it be through our school, one that we're at, or ones just on the internet or whatever, or at other places where races are determined by just tenths of a second, hundreds of a second, um, not a whole lot of time. So it doesn't matter how you express these measurements. Okay, so we often deal with very small measurements in chemistry. We tend to not usually use large ones because generally speaking, we don't talk about things that are very large in chemistry, so it wouldn't make sense to do that. So the first learning objective says be able to write numbers in scientific notation. So this is going to answer that. How do you write numbers in scientific notation? You probably up to this point have already done that at some point in your life. Okay, but to understand to be able to do that, we have to know what a couple things are beforehand. So first thing we need to know is what a measurement is. A measurement is a quantity that has both a number and a unit. Okay, so for instance, if I had a ruler in here, and I do, right? Now, this ruler is measured in inches, okay? And it says it's somewhere on the left over here. But if this just had numbers on it and didn't say that it was measured in inches, unless you specifically knew how long an inch was, you wouldn't know what the unit was. If it just had random numbers on it, it probably wouldn't be that effective. Same thing, if you stepped on a scale and it said, let's say it said 200, and it didn't say the unit with it, well, you don't know if that scale is in pounds. You don't know if it's in ounces or whatever it's in. Now you could probably deduct using common sense what it is based on how much you think you weigh anyways. But you have to have a number and you have to have a unit to have a measurement. And in chemistry, in the lab, but just chemistry in general, everything we do involves a number and a unit. Literally everything. Units are extremely important. I would argue that units are more important than the actual number themselves in chemistry, but it is what it is. So some examples here: your height, your age, and your body temperature are all examples of measurements. So if somebody asked for your height and you said 66, like I said, they could probably could figure out you're talking about inches, but you could be in theory talking about centimeters. You could be talking about millimeters. You could be talking about kilometers. Who knows what you're talking about? Could be talking about feet. So yeah, you have to mention that. If you say you're 15 in terms of age, obviously most people can. If somebody asks you how old you are, you're going to tell them how old you are in years, but you could also tell them how old you are in months or days or minutes or seconds. And so it's good to at least have the unit there. And then your body temperature. Obviously, we use Fahrenheit, but in this class, we're going to almost always use Celsius. So talk about that somewhere later in this packet, but not today. So if you were in class the past couple days, I believe, or at least yesterday, I showed you this number, and we're going to talk more about it later in the future. But this number is Avogadro's number. It's a very, very large number, and we don't want to write that ever. We don't want to write that many zeros. It takes too long, so we want to write it in scientific notation. So scientific notation, you get that when a given number is written as a product of two numbers, a coefficient, and a 10 raised to a power. So we're going to go over plenty of examples here in just a moment. But the first one is the 6.02 times 10 to the 23rd. Okay. What that means is you would take a decimal point and move it over 23 places to get to right after the 6. Okay. So you have a coefficient, and the coefficient that you have, the 6.02, you have to have some number in front of the decimal that is between 1 and 9. Okay, so you would not write this as 60.2 right here. It is 6.02. So this first number has to be 1 to 9. Okay, it cannot be a 0 out front, and it cannot be more than a 9 or a 10. It has to be 1 through 9. And then you raise it times 10 to a certain power. Okay. So this is what I was just saying. The coefficient is always a number greater than or equal to 1 and less than 10. All right. And the exponent has to be an integer. So times 10 to the 23rd, 23 is an integer. The integers are, counting numbers 1, 2, 3, 4, 5, 6, 7, etc. Then you can go obviously in the opposite way. You can go -1, -2, -3, and so forth. But it has to be a whole number, an integer. Okay. You can't have 6.02 times 10 to the 23rd and a half. All right. That's what that's saying. So, a positive exponent indicates how many times the coefficient must be multiplied by 10. And a negative exponent indicates how many times the coefficient must be divided by 10. So, you move it to the decimal place to the left if it's negative, and you move it to the right if it's a positive exponent. Okay. So here are some examples right here that are on your paper. So you have 6,300,000, which is this number right here. And so we're going to move that over 1, 2, 3, 4, 5, 6 places, right? And it's going to be 6.3 times 10 to the 6th. All right. So you have this number, then you need to, I went right to, or left to right, but you need to go right to left. So you need to move it all the way over to here. And then you move it over 6 places, so it's times 10 to the 6. Same thing here. 1, 2, 3, 4, 9.47 times 10 to the 4th. Okay. So this is a little messed up, but it's kind of close. Numbers less than 1 have a negative exponent when written in scientific notation. The value of exponent equals the number of places the decimal has been moved to the right. So it's just the opposite of the one you just saw. Okay. Now, this is going to go over multiplying and dividing, but whenever we do need to do that, we can just put it in the calculator. So these rules, although they are important, it would help you maybe prevent you from putting in the calculator wrong and then getting a wrong answer. At least it would help you to show you, hey, this doesn't look right to me. But you can put it in the calculator always, so it's not a huge deal. But if you have these two numbers, you multiply the 3 times 2 first to get 6, and then the 10 to the 4th, 10 to the 2nd. If you're multiplying these numbers in scientific notation, you add the exponents here to get 10 to the 6th. Same thing here. You got 3, and then you got to the -7. So you add 3 plus -7 or -7, and that's how you get this number. Okay. So moving on, dividing is kind of the same concept. You divide these numbers first, and then you subtract. Instead of add these exponents, you subtract them. But of course, you're going to be able to have a calculator. So as long as you can put in the calculator right, it's not a really big deal. Okay. So same thing for addition and subtraction. I'm just going to kind of skip over this because you can just put it in the calculator. Okay. So solve each problem and express the answer in scientific notation. Okay, so you should pause this video now and you should practice these before you see the answer here. All right, so just put it in the calculator exactly how you see it, both of these, and then check your answer. Okay, so I want to show you the answer right now. Okay, so for the first one, 8 times 7 is 56. 10 to the negative second times 10 to the negative fifth right here, these two. You need to add them up. So that's -2 plus -5, or subtract 5. So -7. 8 times 7 is 56, but you moved it decimal place one place extra over. So it makes it from the -7 to -6. Once again, for the third time, just put it in the calculator correctly and you're fine. Okay. Same thing here. Add these up, just put it in the calculator. Hopefully you did this right, and you get 7.6 times 10 to the negative second. Okay. You can always check your answers too. So the mass of one molecule of water written in scientific notation is 2.99 times 10 to the negative 23rd gram. It's very small. What is the mass in standard notation? You don't have to write this, but that's a very, 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 very small number. So small that you can't, I mean, we can't visualize how small this is. Nothing you've ever seen in your life is this small. So it's just small. You don't want to write all those zeros. That gets tiresome. That's going to take up your whole paper. So we write scientific notation to make things easier on ourselves, and it's just the right thing to do. It just looks better and it's quicker. All right, so we're going to transition from scientific notation, and you're going to practice that a little bit in Edpuzzle that's associated with this, but you're also going to practice it on Monday and Tuesday as well. So how do you evaluate accuracy and precision? Like I said when this video started, it is very easy to get accuracy and precision confused. Okay, so we're going to talk about both. We're going to compare both, and then you're going to have to apply it to not only chemistry but some things in life as well, because you use these words, or at least you think about these words probably every single day at some point, and it applies. This is a part of chemistry that definitely applies to your life. So in chemistry, the meanings of accuracy and precision are definitely different. That's why we don't want to confuse the both. We want to make sure we know each one. Okay, you will definitely need to know both of these. Accuracy is a measure of how close a measurement comes to your actual or your accepted value. Okay, so accuracy starts with A, actual and accepted start with A. Okay, so it's how close you are to what is supposed to happen. All right, so for instance, you would say you're accurate or not based on your grade on a test. So if 100 is being accurate on a test, well, if you take one test and you get a 50, we wouldn't really consider that to be accurate because that would be half. You wouldn't have done that well on it. So that's how you can relate accuracy to some stuff that's not chemistry, but we'll talk about chemistry stuff too. And precision. Precision is a measure of how close a series of measurements are to one another, irrespective of the actual value. So precision doesn't care about what it's supposed to be. It just cares about if it happens over and over again. Okay. So what I'm going to do is I'm going to pause this and I'm going to show you this in. Okay, so they used to call me LeBron James back in high school. I'm going to show you what accuracy and precision looks like in terms of just throwing a ball into that nice recycling bin that is probably pretty dirty. Okay, so I'm going to shoot 5 times, and you can predict right now how many of the 5 you think I'm going to make, and we'll see if I'm accurate or precise, or both. Okay, so all right, that didn't go too well. All right, number 2, 3, 4. And finally 5. Let's see if I can make one. So clearly, I was not very accurate. Example I have of a measurement, the measured value must be compared to the correct value. To evaluate the precision of a measurement, you must compare the values of 2 or more repeated measurements. So to compare precision, you have to have at least 2 things to compare it to. And really having 2 is not that good. You need to have multiple. It's kind of like stats. You need to be able to, have many different trials of something to consider it precise in terms of a lab and stuff like that. So it does give an example of a dartboard right here. So if I throw 3 darts, like I was trying to do a few minutes ago, and they all 3 hit the dartboard in the middle, I have good accuracy, because that's what you're supposed to do, and I have good precision, because they're all right next to each other. I can also have poor accuracy and good precision, which is the one in the middle right here, the 3 that are at the top, or I could have poor accuracy and poor precision, where they're just all over the board, not where they're supposed to be. So the only example that's up here, the only option that's not up here would be good accuracy and poor precision. That's kind of hard to do. You can do it, but it's kind of hard to do, or at least visualize as much as these other 3. Because if you're going to be accurate, mostly you are usually going to be pretty precise, but not always. So how this relates to actual chemistry, accuracy and precision, it actually goes into the accepted and experimental value. So every single time, and hopefully it's quite a bit this year, but I'm not too confident still, that you do a lab in chemistry, you're going to have an accepted value and you're going to have an experimental value. And really, you have these in life as well. You have an accepted value and you have an experimental value. The accepted value is the correct value based on reliable references of a measurement. Okay, it is what is supposed to happen. All right. So when you mix a certain amount of baking soda and a certain amount of vinegar, there's a certain amount of carbon dioxide gas you can produce. It is mathematically found out. You can figure out how much gas you're going to produce, but how much you actually are able to collect and produce is a different story. That's the experimental value. That's what you do yourself. Okay, so accepted value is what it's supposed to be. Experimental value is what actually happens. Is how I would put it in different words. Okay, so we call the difference between these two the error. Okay, and that's going to lead us to the percent error. So the experimental value minus the accepted value is the error right there. Okay. Now, error can be positive or negative depending on whether the experimental value is greater than or less than the accepted value. Okay. So I kind of skipped over this, so I'm going to go back to it, so my bad. Suppose you use a thermometer to measure the boiling point of pure water at standard pressure. Okay, the thermometer reads 99.1 degrees Celsius, but the true boiling point of water is 100 degrees Celsius. So what it truly is 100 degrees Celsius. That is the accepted value. That is what it is. That is scientifically correct. Okay, that's a reliable source. But what actually happens, what it is when you do it, is 99.1. Okay, so the 99.1 is the experimental value. The 100 is the accepted value. And when you subtract these based on this formula right here with the error, you get 0.9 degrees Celsius as your error. Okay. And then it is useful to take that error and then figure out a percent error. That is what is so important in chemistry. It's very, very important in chemistry to figure out the percent error of what you're doing. It tells you how close you were. It pretty much tells you how good you are, how much you suck at something, essentially. Okay. So, and we generally want to make the percent error about 15-ish percent. Okay. That's what we like. We like to have about 15% error. Okay. So the percent error is the absolute value of the error over the accepted value, and we're going to multiply that times 100. Okay. So the percent error of a measurement is the absolute value of the error divided by the accepted value multiplied by 100%. Okay. So that is that. We're going to do a few problems real quick with that. I'm going to transition my camera to my paper. We're going to practice one together. Okay. So you will have some to practice on your own as well with this video over the weekend. Okay. So let's do this one first, though. That's on the screen. The boiling point of pure water is measured to be 99.1 degrees Celsius. So let's calculate the percent error. Okay. And it's a nice guy right there. So the experimental value, what was actually measured, is 99.1. The accepted value is 100 degrees Celsius. Okay. So if you've never done percent error before, and I can't imagine you've not done it in math before, because it's something that, at least when talking about standard deviation and things like that, I would expect you all to have done. The accepted value is 100 degrees Celsius. So we're going to take the percent error is the absolute value of the error. Okay, so it's going to be, if we go back and look at it, the error is experimental minus accepted value, okay, over the accepted value times 100%. Okay, so let's look and see what those numbers are. Okay, so percent error, experimental minus accepted. Okay, we make that absolute value because we want to make it positive if it happens to be negative over the accepted value. So we got 99.1 degrees Celsius is the experimental value, which we already talked about, minus 100, which is the accepted value, absolute value of that, okay, over 100 times 100%. Okay, so what that means for this problem is the percent error is 0.9% after you do this math, which, to be fair, is actually pretty good. If you do a lab and you get a 0.9% error, you did really, really, really good. You did a good job. So remember this. You may want to type this out or write it down. We generally want to be 15% or under. That is the number, 15%. Okay. So if your error is 15% or under, you've done a pretty good job. So are precise measurements always accurate? Other than us practicing some problems in just a moment, this is going to be the end of the content. I'm going to wait until Monday and Tuesday to go over significant figures with you all in class. No, measurements are precise if they are easily reproducible, but not accurate if they do not reflect the accepted value. So precise measurements definitely are not always accurate. Okay. For instance, you could come late to school. Like the accepted value for coming to school would be coming to school on time, right? You can come to school 10 minutes late every single day forever, and you're not accurate with your time of getting to school, but you're pretty precise with your being late to school with the time that you get here. So, all right, I'm going to transition now to my paper, and I'm going to write a few more that we're going to do. We're supposed to make 400 this week mowing lawns. Okay, but you actually got paid 320. So you're supposed to make 400 this week mowing lawns. Keyword supposed. Okay, but you actually got paid 320. What is the percent error? So what we need to figure out, the 400 and the 320. Okay, which one of these is the accepted value and which one of these is the experimental value? Okay, so the accepted one is the one that was keyword supposed to happen. So you are supposed to make 400 this week. Okay, but you actually, what really happened was 320. So that's the experimental. Okay, so let's use the formula we just talked about. Experimental 320 minus accepted 400. Okay, I probably should put the money sign here. Okay, these are absolute value, not a 1, over the accepted, which is 400, and then we multiply this by 100%. Okay, so we actually cancel out our units, which is a good thing, because we should cancel out our units because the percents do not have units. So this is going to be 80, well, negative 80, but the absolute value cancels that out. Okay, over 400, and then we multiply that times 100%. Okay, that's going to be 20%, or a fifth. Okay, so let's think about this. Let me move this other way so you can see it. Let's think about this. Okay, you were supposed to make 400 mowing lawns this week, but what really happened was $320. So there was a 20% error in the amount of money you made this week from mowing lawns in the wrong direction. That's not a good thing. If you're supposed to make 400 and you really get paid 320, that's not good. Okay, that's a 20% error in the wrong direction. All right, so that's the one on your paper. Okay, I'm going to do one more for you. All right, and then we're going to write some stuff in scientific notation, and we'll be done. Okay, so let's say that you did an experiment in the lab, and you were supposed to make, let's say you're supposed to make 15.6 grams of hydrogen gas. Okay, you're supposed to make 15.6 grams of hydrogen gas. Okay, that is what was supposed to happen. Okay, but what actually happened, for some reason, you made 18.5 grams of hydrogen gas. Okay, that's what actually happened. That's what really. These are words that indicate the experimental value here. Okay, so this is the accepted value. That's what was supposed to happen based on science, and this is the experimental value. This is what was, or what did happen based on what you did yourself. This number does not change per person. This one would change per person. So if everybody in the class did this lab and was supposed to produce hydrogen gas, everyone's supposed to produce that amount of gas. Okay, but this number could vary per person. This number is not going to, because it's the same for everybody. It's what everybody is supposed to get. This one would be different. Okay, so experimental 18.5 grams minus the accepted. So I'm actually going to write it out so you see it. Experimental minus accepted over accepted. Okay, times 100%. Now that is a formula that you do need to memorize, but I'm going to let you all use note cards on this next exam as well, and so forth. So that's something I would write down. Okay, so experimental minus accepted over accepted, and then times 100. Okay, so let me get my calculator real quick. 18. See if I can show you this. 18.5 minus 15.6. Okay, divided by 15.6 times 100. Okay, so the percent error here that you had, so you had 2.9. Okay, so let me just go through it one more time so you can maybe understand. 18.5 is the actual value. Okay, or not the actual value, sorry, the accepted value, and 15.6 is what was supposed to happen. So when you subtract those, you get 2.9. You divide that number by what the actual value is, which is 15.6, and then you multiply this by 100 to get a percent. So that's 18.6%. Okay, so that is the percent error. Obviously, you want the percent error to be as close to as you can to 0, but we generally say it's good if it's under 15. Okay, having an 18.6% error is not that bad, but it's also not that good. Okay, remember the cutoff. This will be on the next test, guarantee it. The cutoff is 15%. Okay, above 15, just close to 15, not too bad, but really 15 and under is what you're shooting for when you do a chemistry lab. Okay, not just in high school, but in college as well. So, because obviously we're not machines, but